All set.
Nice to meet you.
Meet you.
So, tell us a little bit about the philosophy of Avalanche, if you have a philosophy.
We do. We got a couple of them. So we started off getting excited about fusion and trying to decide which architecture we're going to put our lives behind. It wasn't just a job, but it was like, if I'm a switch, I'm on or off. There's no dimmer. So what am I going to be dedicated to? And we got evaluating all the ones out there, and we're like, they're too big. They're going to take too long. That's not our experience, my personal or my co-founder's experience in developing technology.
Which technology did you come out of?
Great. So right before this, it was aerospace. So we were working at one of the new space companies developing an orbital rocket. And it was baby steps. It was step by step. Prove something out, learn how it works, take the paper model, see how it performs, learn how to build it, and all the little real world things that you didn't put into your assumptions and how they impact it. So we started small. It was like we decided we need to do something small.
But as I understand it, you're kind of staying small in some ways, right? I mean, the devices you're making are, not the size of city blocks. You could fit more than one of them on a submarine.
No, it's going to stay there. The start small is like the philosophy. It has to be small. So small for shortened iterations between your prototypes. First one, test it, learn from it, know how to build it. How did it fail? Where did your assumptions and your simulations go wrong? Iterate on it. The tighter that can go, the faster your learning can be. But it also had an economics aspect to it. And you hear about supply chain here. And I was terrified of that. I've worked on projects where scale reduced the supply chain. There's certain step changes where you just can't get the components or the raw materials anymore. But when you can make it in-house, or you have the small enough components that you can get the high quality that you need, that enables those iterations, helps you go faster.
So how small are we talking? Your current devices?
Yeah. So the plasma core for our devices are a 12 centimeter inner diameter right now. Probably not a commercial product in that size. It's going to be on the meter, 2 meter diameter. But that's where full physics allowed us to fully understand the device, have enough space to put diagnostics on it, and be able to get machining centers and the technologists and technicians building it, within months.
And in terms of the triple measure that we were hearing about earlier, where have you got to?
I don't know what a 0.01. It's low right now. So we broke them into 3 different aspects. So you want that long confinement time of something that's really high energy to have a good fusion cross section, and then you want good density there. And so small also helped us be able to build 3 test cells where we're able to. How we densify it was with an electron confinement. We had one just doing electron confinement. We had one just loading the ions. We had just one doing the confinement time and increasing the amount of time that we keep those ions in there.
And do you have a way to market with these smaller devices before you get to actual power fusion, as we were just hearing about?
Yeah, so that's part of the step, that we saw that you need to for the long term. You're always going to run into things that you don't understand or didn't plan in developing something. If that's engineering rockets, where we fully understand the science, we know they work, we've been to the moon, or something that's a little bit, yet proven. So to be able to weather that, not only from a team perspective and a technology perspective, but revenue-wise, being able to use a fusion product soon. So I was hoping to be able to say it today, but we've got an announcement coming out Thursday to that effect, of where we've got some partnerships and facility we're standing up to be able to use those neutrons.
Well, I'm sure I speak for everyone. We're terribly disappointed that you can't. I mean,
I am too.
I was going to say there aren't any journalists here, but that really wouldn't be true. So, but well, that sounds exciting to look forward to. And we were also talking just before about space. And this is your background. Is space-based an area that you're interested in?
Very much so. So it was kind of funny when we quit the first day we quit our aerospace job. We went out and we had a celebratory lunch, and we were sitting there, and I had this space shirt on, and the waitress was like, "Oh, do you work on rockets?" I said, "Not anymore. We're doing fusion." And she goes, "Ah," and she walked off, and she wasn't interested.
And then seems to be a subtle theme of the whole session.
We're still trying to get people excited about it. It hasn't hit all the lay people yet. But right after that, we got a contract to start doing some studies for space. So that high density in a mobile package is, very interesting to a lot, but the capability-driven defense industry primarily, not only for the power though, but for the neutrons again for imaging.
And it's such a different approach to the people who are talking about making, leaving aside ITER, but making big tokamaks with huge amounts of simulation and hundreds of millions of dollars. Do you find it hard to, I don't know how to put this polite, how do you find it hard to get taken seriously?
No, I think I was pretty polite. I've said it before. It's like sometimes I'll talk to people and I feel like a rock star at tackling this big problem. Sometimes I feel like a snake oil salesman. And I think everybody that's been through like starting a scrappy company that's got some principles, they've got some advocates and some wind on the back, but they're going to be facing a headwind for a long time to convince. On both, it's demoralizing sometimes, but it's also inspiring. Like not that far from here, Frank Whittle's, jet development was like that. Like the early, solar and nuclear. I mean, there's a lot of people that were not, believers in it in the beginning. So I think that's par for the course.
Right. Though that's also true, for instance, for Bob Guccio and his fusion as well. That was started off very small and stayed small. But I must admit, I had exactly the same reaction that most people might have, and I got in touch with someone who knows your company and says, "Are these people for real?" And I said, "Oh yeah, you've got to go and visit them. You don't get it until you visit them, and see the lab." Is he unusual in that respect, or do you find that people take it much more seriously when they actually see your case?
No, that's the thing I'm always telling people is like, come out, see the lab. Like you can look at PowerPoints. I'm not moved by them. You see LinkedIn messages, people trying to sell stuff to me. I don't believe it's real either until you see 50 people that are building these things. So, it comes down to principles-based approach. It's like you need to have that triple product and you got to show legs to be able to get there. We have a device that's not brand new. It's based on an orbit trap. It traps ions for a long period of time. That exists. We densify electrons with like a magnetron. That exists. Putting them together and going to high voltage is the key there. And we've held 300,000 volts in that device that size a couple weeks ago for 5 hours. And it was in the error of measurement of our power supply. So it was less than 20 microamps of power to do it. So that's exactly what we need to do. That voltage gets us the energy in the ions for a good cross section. It's actually the peak cross section, well beyond it for deuterium tritium. So when you see that and you see the devices doing it, you get a little bit more excited and say, all right, maybe I'm going to dig in a little deeper.
Okay, are there any questions for Brian? About the general approach, or I do find this approach of trying it out and seeing what works and iterating really quickly.
I would highlight that it's not just experimenting. There is a lot of simulation work. Our cloud computing fees are very, very high, so we don't go into these experiments with just a wish and a prayer.
Right.
There is expectations on them, and we validate what we're doing pretty often.
So I'm looking for questions. I'm looking on Slido. Are you tired? Are you intimidated?
Well, I'll tell a story then.
Okay, you tell a story.
So why it's important to test this. So you make a lot of assumptions. There is a lot of particles moving in there. It's difficult to be able to predict everything that's going to happen. You simplify your models. And then when you put it in, we find you may sputter off ions and they deposit somewhere else, or they build up charge on ceramics and they change how your beam or how your confinement works. Or this last week, I wasn't ready to post it, but my co-founder did. I don't know what happened with our ion injector, but it looks like a lightsaber stuck into the diagnostics inside there. And so it's nice to be able to laugh at that, because I know my machinists can turn it around in a day. If I didn't know they could turn it around in a day and we'd be waiting 9 months, I'd have a team of people evaluating absolutely everything we did. And we'd enter into this analysis paralysis because we're scared of the schedule or the cost impacts. But we can turn it around and we can fix it. So we move forward with 50-70% of the information. Test it, validate the model.
So a question from Slido. Tell us about the DeLorean.
So I had my radiation safety officer come and tell me that the Nuclear Regulatory Commission wanted to meet with us because they heard about a reactor on a car on a boat. And that was alarming to me too, and I didn't know what was going on. Last year, San Francisco, we had a booth, and it turned out we found somebody with a DeLorean and had it decked out like a time machine. We stuck our mock-up on there, and then they changed the venue and they moved it onto the USS Hornet. So we had a DeLorean with our mock-up reactor on an aircraft carrier, and then through a game of telephone, we had a tense meeting with the NRC. And then we laughed, and they didn't know why we were laughing, and we had to reel it back. Like, no, everything's okay.
Do you worry about, or do you bank on the idea that this will be a military technology?
In the beginning, yeah, I think so. Like a lot, MRIs, solar panels again, GPS, ARPANET was a precursor to internet. So I do believe that, you start off at low production, high cost. And fusion's not going to be any different. And that's scary when you're trying to sell electrons to a grid. Those are commodity prices. Most people will be like, yay, fusion. But like, look, I just want the light to go on. I can't tell if it's fusion electrons that showed up. So I think that's the right start until you're able to iron it out, make it more designed for mass manufacturing, get those big supply chains, and then you've got the gigafactories. So then it's low cost, high production. So.
And on the DeLorean point, you're starting small because that's the way to do the engineering. But how small could a viable fusion machine be? Where could you? I mean, I don't actually know what the power rate of a car engine is. I did know once, but it's in the sort of like kilowatts or megawatts. Bob's not here.
Yeah, so I don't see it probably powering cars. We're probably about 15 kilowatts all in, something the size of like a wine barrel. You could power a car on it, but your acceleration would be incredibly slow. So it's not a high density power, it's high density energy. So if you just had the Fusion one, you would just be, fighting that headwind. You got to cruising speed, then you cruise on the highway for 4 years. So it's a little bit different there. It's great for autonomous underwater vehicles for monitoring. They don't have another good way to be able to get power or space. So those really remote applications are the first ones for power. And before that, again, neutrons for imaging and remote sensing.
Great. Well, Brian, thanks very much indeed.
Thank you all.
Very nice talking to you.